Assalamualaikum and hi guys! Today I will discuss about subtopic in orthogonality in Rn. So let's check it out. So what is orthogonality? Two vectors in a vector space considered orthogonal if they are perpendicular to one another. When we talk about perpendicular, the angle between two vectors is half parallel or 90 degree. This situation occurs when the dot product is equal to 0. Since the dot product is equal to product of two vector lengths times with cosines of the angles between them and the cosines of half pi is 0, which makes the dot product of x and y is equal to 0. So, right now, we're gonna talk about orthogonal set. What is an orthogonal set? The concept of orthogonality is a central idea in geometry, occurring as it does in Pythagoras' theorem, in the notion normal to a plane, and in the way we find the point on a line that is closest to a given point. In Pythagoras' theorem, we will let the set of vector x1, x2 until xk be an orthogonal set of vector Rn. So, when we square the set of vector of x1, x2 until xk, we will get x1 square plus x2 square and so on. Right now, we will prove the fact that the dot product of xi and xj is equal to 0 whenever I is not equal to j. So, we will square the set of vector of x1 plus x2 and so on. So, after we square that the set of vector, we will get this one. So, after we expand this one, we will get this one. So, this will prove that the theorem, which is the dot product of xi and xj, is equal to 0 whenever I is not equal to j. Next, we want to talk about corollary theorem. Let vector v and w be a non-zero vector in R3. There is two conditions we must know in corollary theorem, which is the first one is the set of vector v and w is linearly dependent if and only if vector v and w are parallel. And the second one is when the sets of vector v and w is linearly independent if and only if vector v and w are not parallel. So, the conclusion is the orthogonality turns out to play an even more important role in the geometry of Rn. Moreover, as for the length and distance, the definition is a natural extension of situation in R3, which that when the vector x and y in Rn will be orthogonality when the dot product of x and y is equal to 0. A set of vector x1, x2 until xk is called an orthogonal set of vector if the dot product of xi and xj is equal to 0 for all I is not equal to j, while xi is not equal to 0 for all I.
So the first example, as we see on the statement here, which is there is three vector, 1, 0, negative 1, 1, set 2, 1, and 1, negative set 2, 1 is mutually orthogonal. So how can we prove that these three vector is mutually orthogonal? So first step, we have to let the first vector is equal to v1, second vector is equal to v2, and the third vector is equal to v3. And then we have to verify whether the dot product of v1 and v2 is equal to 0 or not. If the dot product of v1 and v2 is equal to 0, then it is orthogonal. So the calculation is, as we see like this, So 1 times 1 plus 0 times set2 plus negative 1 times 1 is equal to 0. So it is proof that the dot product of V1 and V2 is orthogonal because the summation of this is equal to 0. And then we have to verify whether the dot product of V2 and V3 is equal to 0 or not. So as we see here, V2 and V3, 1 times 1 plus set2 times negative set2 plus 1 times 1. So the summation of this calculation is equal to 0. It is proof that the dot product of V2 and V3 is equal to 0, then it is orthogonal. And then we have to verify the dot product of V1 and V3 is equal to 0 or not. So as we see here, 1 times 1 plus 0 times negative set2 plus negative 1 times 1. So the summation of this calculation is equal to 0. So it is proof that the dot product of V1 and V3 is equal to 0, then it is orthogonal. Therefore, it shows that the vectors V1, V2 and V3 are an orthogonal set of vectors in R3. So for example 2, we have to verify whether S is an orthogonal set of vectors where S is equal to the set vectors of U1 and U2 and U3, which is U1 is equal to 1, 0, 1, 2 and U2 is equal to 1, 1, negative 1, 0 and U3 is equal to 1, negative 2, negative 1, 0. So if we use the notation S equal to U1, U2 and U3, then the same step actually we have to verify whether the dot product of U. So for example 2, we have to verify whether S is an orthogonal set of vectors where S is equal to the set of 3 vectors, which is this is the first vector 1, 0, 1, 2 and this is the second vector 1, 1, negative 1, 0 and this is the third vector 1, negative 2, negative 1, 0. So we denote as, we let as the first vector is equal to U1, the second vector is equal to U2 and the third vector is equal to U3. So the same step actually we have to verify whether whether the dot product of U1 transpose and U2 is equal to 0 or not. So like this, 1 times 1 plus 0 times 1 plus 1 times negative 1 plus 2 times 0 and the summation of this calculation is equal to 0. So the dot product of U1 transpose and U2 is orthogonal because the dot product of U1 transpose and U2 is equal to 0. And then the same step we have to verify whether U1 transpose, whether the dot product of U1 transpose and U3 is equal to 0 or not. So like this, 1 times 1 plus 0 times negative 2 plus 1 times negative 1 plus 2 times 0. So the summation of this calculation is equal to 0. So it is proof that the dot product of U1 transpose and U3 is orthogonal. And then we have to verify the dot product of U2 transpose and U3 is equal to 0 or not. So like this, we calculate 1 times 1 plus 1 times negative 2 plus negative 1 times negative 1 plus 0 times 0. So the calculation of this, so the summation of this calculation is equal to 0. It is proof that the dot product of U2 transpose and U3 is orthogonal. Therefore, S is equal to the set of vector U1, U2 and U3 is an orthogonal set of vectors in R4. So the third example, we have to determine whether the given set of vectors is orthogonal. So the first vector is -1, 4, 3. Second vector is 5, 2, 1. And the third vector is 3, -4, -7. So we let as A1 is equal to first vector, A2 is equal to second vector, A3 is equal to third vector. And then the same step, we have to verify whether the dot product of A1 and A2 is equal to 0 or not. So as we see like this, -1 times 5 plus 4 times 2 plus 3 times 1. So the summation of this calculation is equal to 6. It is proof that the dot product of A1 and A2 is not orthogonal. And then, second step, we have to verify the dot product of A1 and A3 is equal to 0 or not. So as we see like this, -1 times 3 plus 4 times -4 plus 3 times -7. So the summation of this calculation is equal to -40. So it is proof that the dot product of A1 and A3 is not orthogonal. And then we have to verify the dot product of A2 and A3 whether it is equal to 0 or not. So as we see like this, 5 times 3 plus 2 times -4 plus 1 times -7. So the summation of this calculation is equal to 0. So in this case, it is proof that the dot product of A2 and A3 is orthogonal. Therefore, the given set of vectors is not orthogonal set of vectors in R3 because the dot product of A1 and A2 and the dot product of A1 and A3 is not equal to 0. That's all from me. Thank you. Bye.